Welcome to our deep dive into Maxwell's equations, the foundation of classical electromagnetism. These four elegant equations, formulated by James Clerk Maxwell in the 19th century, describe how electric and magnetic fields interact and propagate through space. Today we'll explore each equation, understand their significance, and see how they shape the world around us. Whether you're a physics enthusiast or just curious about the forces that govern our universe, this journey will illuminate the invisible threads connecting electricity, magnetism, and light. Let's begin by setting the stage for these groundbreaking discoveries and why they matter in both science and everyday life. Before we delve into the equations themselves, let's take a moment to appreciate the mind behind them. James Clerk Maxwell was a Scottish physicist whose work revolutionized our understanding of electromagnetism. His insights unified electricity and magnetism into a single theory, paving the way for modern physics. Maxwell's equations not only explained existing phenomena but also predicted the existence of electromagnetic waves, which include visible light. His legacy continues to influence technology from radio to smartphones. Understanding the man helps us appreciate the profound impact of his work on science and society. Maxwell's equations consist of four fundamental laws: Gauss's law for electricity, Gauss's law for magnetism, Faraday's law of induction, and Ampere's law with Maxwell's addition. Each equation describes a different aspect of how electric and magnetic fields behave. Together, they form the backbone of classical electromagnetism, explaining everything from how light travels to how electric motors work. In the following scenes, we'll break down each equation, explore its meaning, and see real-world examples of its application. Let's start with Gauss's law for electricity. Gauss's law for electricity states that the electric flux through a closed surface is proportional to the charge enclosed within that surface. In simple terms, it tells us how electric charges create electric fields. Imagine a balloon with charges inside. The total electric field passing through the balloon's surface depends on the amount of charge inside. This law is essential for understanding phenomena like static electricity and the behavior of conductors. It's the starting point for analyzing electric fields in various situations, from atoms to capacitors. Better understand Gauss's law, let's visualize electric flux. Picture lines radiating outward from a positive charge representing the electric field. The number of lines passing through a surface like a sphere indicates the flux. If you increase the charge inside, more lines pass through. This visualization helps us grasp how charges influence their surroundings and why the law is so powerful for calculating electric fields in symmetrical situations. Gauss's law isn't just theoretical, it's used in practical applications every day. Engineers rely on it to design capacitors, which store energy in electric fields. It's also vital in understanding how charges distribute themselves on conductors, influencing everything from lightning rods to electronic circuits. By simplifying complex problems, Gauss's law allows us to predict electric field behavior in a wide range of technologies. Second equation, Gauss's law for magnetism, states that the net magnetic flux through any closed surface is zero. This means that magnetic monopoles, isolated north or south poles, do not exist in nature. Magnetic field lines always form closed loops, emerging from the north pole of a magnet and entering the south pole. This law is crucial for understanding why magnets always have both poles and why magnetic field lines behave the way they do. Let's visualize magnetic fields using iron filings around a bar magnet. The filings align along the invisible magnetic field lines, showing the closed loops described by Gauss's law for magnetism. No matter how you cut a magnet, you always get both a north and a south pole. This visualization helps us see why magnetic monopoles haven't been found and why magnetic fields behave differently from electric fields. Understanding magnetic fields is essential for countless technologies. Electric motors, generators, and transformers all rely on the principles described by Gauss's law for magnetism. Magnetic resonance imaging, MRI in medicine, and data storage in computers also depend on our knowledge of magnetic fields. This law helps engineers and scientists design devices that harness magnetic forces for practical use. Faraday's law of induction is the third of Maxwell's equations. It states that a changing magnetic field induces an electric field. This principle is the foundation of electric generators and transformers. When a magnet moves near a coil of wire, it creates a current in the wire. Faraday's law explains how we convert mechanical energy into electrical energy, powering everything from power plants to bicycle dynamos. See Faraday's law in action. Imagine moving a magnet through a coil of wire. As the magnetic field changes, an electric current is generated in the wire. This simple experiment demonstrates how changing magnetic fields can produce electricity, a process at the heart of modern power generation. Visualizing this helps us understand why Faraday's discovery was so revolutionary. Faraday's law is everywhere in our daily lives. It's the principle behind electric generators and power plants, which supply electricity to homes and businesses. It also powers induction cooktops, electric guitars, and even wireless charging devices. By understanding how changing magnetic fields induce currents, engineers have created countless devices that make modern life possible. Fourth equation is Ampere's law, modified by Maxwell to include the displacement current. It states that magnetic fields are generated by electric currents and by changing electric fields. This addition was crucial for predicting electromagnetic waves such as light. Maxwell's insight unified electricity, magnetism, and optics, showing that light itself is an electromagnetic wave. Visualize Ampere's law. Picture a wire carrying electric current. Magnetic field lines form concentric circles around the wire. If the current changes, the magnetic field also changes, and Maxwell's addition accounts for this effect. This visualization helps us understand how electric and magnetic fields are intertwined, leading to the concept of electromagnetic waves. Ampere's law is fundamental to the operation of electromagnets, transformers, and inductors. It's also key to understanding how electromagnetic waves are generated and transmitted. From MRI machines to radio antennas, this law underpins technologies that shape our world. Maxwell's addition made it possible to predict and harness electromagnetic waves for communication and imaging. One of Maxwell's greatest achievements was showing that light is an electromagnetic wave. By combining his equations, he predicted that oscillating electric and magnetic fields could travel through space at the speed of light. This discovery unified the fields of electricity, magnetism, and optics, revealing that visible light, radio waves, and X-rays are all part of the same electromagnetic spectrum. Electromagnetic spectrum includes all types of electromagnetic waves, from radio waves to gamma rays. Maxwell's equations explain how these waves are generated and how they travel. Understanding the spectrum helps us use different types of waves for communication, medical imaging, and even cooking. The spectrum is a testament to the power and reach of Maxwell's insights. Maxwell's equations are the foundation of countless modern technologies. They govern the operation of radios, televisions, cell phones, and Wi-Fi networks. Engineers use them to design antennas, fiber optics, and satellite communication systems. Without Maxwell's work, our connected world would not exist. His equations continue to drive innovation in fields ranging from telecommunications to medical imaging. Maxwell's equations can be written in both integral and differential forms. The integral form relates to the total effect over a surface or loop, while the differential form describes the behavior at a single point. Both forms are used in physics and engineering to solve real-world problems. Understanding the math behind the equations helps us apply them to complex situations, from designing circuits to modeling electromagnetic waves. Field lines are a powerful way to visualize electric and magnetic fields. They show the direction and strength of the fields, helping us understand how they interact with charges and currents. Surfaces like spheres or loops are used in the integral forms of Maxwell's equations to calculate flux and circulation. These visual tools make abstract concepts more concrete and accessible. Permittivity and permeability are constants that appear in Maxwell's equations. Permittivity relates to how electric fields interact with materials, while permeability describes how magnetic fields behave. These constants determine the speed of electromagnetic waves in different media. Understanding them is essential for designing materials and devices that control electric and magnetic fields. When electric or magnetic fields encounter boundaries between different materials, they must satisfy certain conditions. These boundary conditions are derived from Maxwell's equations and are crucial for understanding phenomena like reflection, refraction, and transmission of waves. Engineers use these principles to design lenses, coatings, and waveguides for controlling electromagnetic waves. In free space, Maxwell's equations predict the existence of electromagnetic waves that travel at the speed of light. These waves consist of oscillating electric and magnetic fields perpendicular to each other and to the direction of propagation. This prediction was confirmed by experiments and forms the basis for understanding light and radio waves. Polarization describes the orientation of the electric field in an electromagnetic wave. Maxwell's equations explain how polarization arises and how it can be manipulated. Polarization is important in technologies like sunglasses, LCD screens, and wireless communication, where controlling the direction of the electric field enhances performance. When electromagnetic waves encounter a boundary, they can reflect or refract depending on the properties of the materials. Maxwell's equations provide the mathematical framework for predicting how much of the wave is reflected or transmitted. This understanding is essential for designing optical devices, fiber optics, and communication systems. Waveguides and fiber optics use the principles of Maxwell's equations to confine and direct electromagnetic waves. By controlling the shape and material of the guide, engineers can transmit signals over long distances with minimal loss. This technology is the backbone of modern communication networks, enabling high-speed internet and global connectivity. Antennas are devices that transmit and receive electromagnetic waves. Maxwell's equations describe how oscillating currents in antennas generate radiation, allowing signals to be sent and received over vast distances. Understanding these principles is key to designing efficient antennas for radio, television, and wireless communication. While Maxwell's equations describe fields, they also underpin circuit theory. Concepts like capacitance, inductance, and resistance are all rooted in the behavior of electric and magnetic fields. Engineers use simplified versions of Maxwell's equations to analyze and design electronic circuits, from smartphones to power grids. Electromagnetic Compatibility (EMC) ensures that electronic devices can operate without interfering with each other. Maxwell's equations help engineers predict and control electromagnetic interference, making sure devices like phones, computers, and medical equipment work reliably in close proximity. To protect sensitive electronics from unwanted electromagnetic fields, engineers use shielding techniques based on Maxwell's equations. Materials like copper and aluminum can block or redirect electromagnetic waves, safeguarding devices from interference and ensuring accurate operation. Wireless power transfer uses the principles of electromagnetic induction as described by Maxwell's equations to transmit energy without wires. This technology powers devices like electric toothbrushes and smartphones and is being developed for electric vehicles and industrial applications. Magnetic resonance imaging (MRI) is a powerful medical tool that relies on the principles of electromagnetism. Maxwell's equations describe how strong magnetic fields and radio waves interact with the body to produce detailed images of internal structures, aiding diagnosis and treatment. Maxwell's equations don't just apply to technology, they also explain natural phenomena. Lightning, the aurora borealis, and even the behavior of the sun's magnetic field are all governed by these laws. Understanding electromagnetism helps us appreciate the beauty and complexity of the natural world. Maxwell's equations predict that electromagnetic waves travel at a constant speed in a vacuum, the speed of light. This revelation connected the study of electromagnetism with optics and led to the realization that light itself is an electromagnetic phenomenon. The speed of light is a fundamental constant of nature. The implications of Maxwell's equations set the stage for Einstein's theory of relativity. The constancy of the speed of light predicted by Maxwell challenged classical physics and led to a new understanding of space and time. This connection shows how foundational Maxwell's work is to modern physics. Maxwell's equations laid the groundwork for quantum electrodynamics (QED), the quantum theory of electromagnetic interactions. QED extends Maxwell's ideas to the quantum realm, explaining phenomena like photon emission and absorption. This theory is one of the most successful in physics, with predictions confirmed to remarkable precision. Researchers continue to use Maxwell's equations to explore new frontiers in science and engineering. From developing metamaterials with unique properties to studying the behavior of plasmas in fusion reactors, these equations remain at the heart of cutting-edge research. Their versatility and power make them indispensable tools for discovery. Educators use a variety of methods to teach Maxwell's equations, from visualizations and simulations to hands-on experiments. Making these abstract concepts accessible helps inspire the next generation of scientists and engineers. Understanding Maxwell's equations opens doors to careers in physics, engineering, and technology. Despite their importance, Maxwell's equations are often misunderstood. Some people think they only apply to advanced physics, but their principles are present in everyday life. Others confuse electric and magnetic fields or overlook the role of displacement current. Clarifying these misconceptions helps build a solid foundation for further learning. As technology advances, Maxwell's equations will continue to play a central role. From wireless energy transfer to quantum computing, new applications are constantly emerging. The ability to manipulate electric and magnetic fields with precision will drive innovation in fields we can only imagine today. To recap, Maxwell's equations are four fundamental laws that describe how electric and magnetic fields interact. They explain the behavior of light, the operation of countless devices, and the structure of the universe itself. Understanding these equations gives us insight into the forces that shape our world and the technologies that define modern life. James Clerk Maxwell's legacy extends far beyond his equations. His work transformed physics, inspired generations of scientists, and continues to shape the world we live in. From the tiniest electronic devices to the vastness of space, Maxwell's insights remain as relevant today as they were over a century ago. For those interested in learning more, there are many resources available. Textbooks, online courses, and interactive simulations can deepen your understanding of Maxwell's equations and their applications. Exploring these resources can open up new perspectives and inspire further curiosity about the world of electromagnetism. Maxwell's equations have even made their way into pop culture, appearing in movies, TV shows, and literature. Their iconic form symbolizes the beauty and power of scientific discovery. Seeing these equations in popular media reminds us of their enduring impact and the fascination they inspire. In conclusion, Maxwell's equations are more than just mathematical statements, they are the language of electromagnetism. They reveal the unity of nature's forces and empower us to harness electricity and magnetism for the benefit of humanity. As we continue to explore and innovate, Maxwell's legacy will guide us toward new discoveries and a deeper understanding of the universe.